So, good day again, students, and welcome to the last and final lecture in the course about biofuel availability and the assessment of biomass resources for energy. The course is now coming to an end, and it's time to summarize what we've gone through during the course, and to outline some conclusions and some challenges that we have for the future. Again, and this cannot be said too often, it must be understood that the biomass in itself has no value in an energy context, but ultimately it's only the energy service that is delivered that counts in the system. There are already many technologies available, and even more technologies are in the developing stage right now. In spite of these technologies that already are available and are upcoming, there are a number of common misunderstandings that act as a hindrance for the introduction of renewable energy and bioenergy. And let's have a look at these misunderstandings. The first very common misunderstanding is that biomass for energy has to be virgin, it has to be fresh from the fields, but this is not true, as we will see. A second common misunderstanding is that biomass for energy must be agricultural, so it must be grown on cropland, which is basically not true. A third misunderstanding comes from the second one, and says that biomass for energy always competes with food. Now, this is not true, as we will soon see. And as a consequence, biomass for energy would also compete with fiber for the production of clothes and cloth that we need in everyday life. Some people would argue that biomass for energy compete with the wood industry, with the timber industry, with the paper and pulp industry. But this is not true. Sometimes you will hear people say that the transport energy for biofuels makes the total energy balance negative, so that the biofuel transports are extremely energy inefficient. This can be discussed. You might also hear people say that the upgrading of biofuels, like pelletizing, is so energy inefficient that the total energy balance after upgrading becomes negative. Obviously, this is not true. You might hear people say that the biofuels can only be used in low temperature processes, such as for steam raising for electricity or alike. Basically, this is not true. The conclusion of the 8 first misunderstandings becomes that biofuel use has a very low total efficiency. Now, this is open for discussion. And the final conclusion out of these misunderstandings is obviously that bioenergy is uneconomical, that it is naive, and that it cannot be used in industrial society. This is not true. It's a false conclusion. So let's go through these misunderstandings one by one. First, must biomass for energy be virgin? No, it doesn't have to be virgin. The main part of the biomass actually used for energy was, before it was used for energy, regarded as waste fractions. Obviously, this is not true for ethanol produced from maize, nor for the use of corn as a fuel, but such abuse of food for energy is quite uncommon, and has been seriously criticized from the international community and the United Nations. So, biomass does not have to be virgin when used for energy. it can be waste fractions. Does biomass for energy have to come from cropland and be agricultural to its origin? No, it doesn't. Certainly, some fractions such as straw, droppings, dung, rice husk, cotton stalks, coconut shells or alike are originally agricultural. But sawdust, clean demolition wood, algae or sewage sludge, just to mention a few, are not agricultural. And they do definitely not compete with the production of food and fiber from agriculture. Will the production of biomass for energy always compete with the production of food? No. Cattle droppings or shavings from wood manufacturing does not compete with food production, just to mention two. Of course, some crops, like straw, may find use as a green fertilizer in the agricultural sector, and the system as a whole must always be evaluated from case to case. But there is no general conflict between the production of food and the production of biofuels. Abuses, such as the use of maize for ethanol production, must of course always be avoided. Is there a conflict between the production of biomass for energy and the production of biomass for fiber? No, there is not. Cotton spills from textile industry or assorted fractions of municipal waste were never used for fiber, nor were algae. Flax stalks may of course be used for both purposes, but the system as a whole must be evaluated from case to case. Does biomass for energy compete with the resource base for wood-based industry, such as paper and pulp industry and timber industry? No, the shavings from wood manufacturing, or the sawdust produced in carpentry, may certainly be used for fiberboard, but there is no general conflict. Again, the situation has to be evaluated from case to case and from region to region. No serious energy engineer would ever advocate the use of whole virgin trees only for energy purposes, instead of using the tree for timber, for pulp and paper, and for energy in combination. Is the need of transport energy for biofuels so large as to render them energy inefficient? Well, it is true that biofuels do require a larger transport energy relative to their energy content than fossil fuels do. Thus, the production plants, the supply chain, and the technology used must be planned, designed, and localized accordingly. No serious energy engineer would ever advocate biofuel-fired plants the same size as those aimed for fossil fuels, and that is because of the transport energy. Is the energy input needed to upgrade the biofuels to a higher quality so large as to render the total energy balance of the biofuel negative? No, it's not. The energy needed for pelletizing, all included, amounts to about 10 to 15% of the final energy in the pellet. The losses in thermal gasification amount to about up to 10 to 15%, but less in large-scale plants, of the total energy in the gas produced. But of course, upgrading should be avoided and used only when necessary or when it adds value to the final product, sufficient added value to pay for the energy input. You will sometimes hear people say that biofuels can only be used for low temperature processes, 700 degrees or lower. Now, this is not true. The flame temperatures with dried biofuels are similar to those of the fossil fuels, like 18 to 1900 degrees Celsius. Hence, biofuels can be used for the same high temperature applications where fossil fuels are today dominant. We need only mention glass manufacturing, steel manufacturing, or the burning of building brick as examples. The important thing to remember is that, for example, biomethane from sewage sludge has exactly the same properties as fossil methane as found in the so-called natural gas. Those people who are subject to the 8 aforementioned misunderstandings will usually arrive at the conclusion that the biofuel use has a low total efficiency. Now, this is not true. But, of course, if biofuels are input into a system solution which is adopted and designed for fossil fuels, and where care is not taken about the special properties of the biofuels, then the total efficiency becomes low. But the scale, the system layout, and the technology chosen are the factors to determine the total efficiency in the system. So, actually, system efficiency is a question of engineering skills, not of the fuel as such. Another false conclusion based on the previously mentioned misunderstandings is then that bioenergy is uneconomical and not economically feasible. But this is not true, because bioenergy use may help to solve the local waste handling problems. It will create local long-term jobs, and it might provide new sources of income for agricultural and forest industry sectors, and in agricultural and forested areas. So then, disregarding all the misunderstandings that we've just mentioned, is bioenergy, and indeed renewable energy as a whole, naive for industrialized nations? Or can it only be used in agricultural nations and more primitive economies? No. Let's look at the Swedish experience as outlined in the diagram in this slide. You will see how the share of renewable energy at the bottom of the diagram has increased steadily for 40 years, ever since the 1970s, and is today a major source of energy in the Swedish energy system, second only to oil and oil products that are mainly used for transport. You will notice that the renewable part of the energy in the diagram is split around 1990, where there's a change of color shade. This is due to a change in the formal way of reporting the statistics. So the statistics are not exactly the same after 1990 and before 1990, but you will anyway see how the tendency remains. Another feature in the diagram is the significant increase of the losses in the energy system during the late 1970s and the early 1980s. This was due to a massive introduction of condensing power production aimed to replace the direct use of oil for industrial process heating and domestic heating. Since condensing power production has a very low efficiency, that led to a significant increase in the total losses, whereas the total use of energy as indicated by the line at the lower end of the losses area in the diagram, has only increased very slightly over the 4 decades since 1970. The diagram on the previous slide indicated how the introduction of condensing power production to replace the direct use of non-renewable oil for heating purposes led to a lowering of the total efficiency in the system. This was because the introduction of new electricity production was not optimized with respect to the customer needs. And when you plan an energy system, or when you plan major changes in the energy supply system in a society, your estimates, your judgments, and your recommendations must always be based on the end user needs of services. The European Commission for Standards in 2003 published a document called CEN TS 14588, which defines a set of terms and the terminology to be used in bioenergy systems. And you will realize from this slide how biomass, biofuels, and bioenergy represent different steps in the supply chain. This course has concentrated on the assessment of biomass resources for energy, so it has been concentrated on the left-hand side of the sequence. We have mentioned some of the conversion technologies that are possible to convert solid biofuels into liquid and gaseous biofuels. And we have touched a bit upon the bioenergy and the final conversion into bioenergy and the supply of energy services. But when you work in the area, you have to have the full picture in your head and never forget that the end user need of energy services is the ultimate point and the reason for the supply system. Let's now just look at a few very simple examples of how different system solutions can be set up to provide cooling and electricity for a society, and what are the possibilities that these system solutions can also provide heat for tap water or for comfort heating. We'll start looking at one of the most common large-scale solutions as found worldwide. That is large scale, so it's larger units than about 500 megawatt thermal power. They would be condensing power stations, using typically, in the modern case, a combined cycle, that is, a gas turbine and a steam turbine in combination. Such a modern power station will have a total electricity efficiency of about 45, maybe up to 50%, and the remaining part of the fuel energy input will be lost. In this Sankey diagram in the slide, we assume 45% electricity efficiency and 55% losses. If the electricity is then input into a compressor cooling station, this will provide a cooling power of approximately 30% of the total fuel input. And it will reduce the electricity delivered to the grid from 45 down to 30%. So ultimately, this system will give a total service provided to the end users of 30% electricity and 30% cooling power, as compared to a fuel input of 100%. The same technology may be applied also with biofuels, but to arrive at these efficiencies you will have to have a gasifier to provide the gasified fuel to the gas turbine, which is the first step. Now, depending on the gas cleaning, if it's a hot cleaning or a cold cleaning, the gasifier will not only complicate the process, make it more expensive and more sensitive, but it will also reduce the total efficiency, because the gasifier comes in before the power station unit. The technology is best suited for large-scale units, more than 500 megawatt fuel input. So, in the case of biofuel, the transport work would be immense, and this is not a very good system solution in a bioenergy supply system or in a bioenergy system. Going to a slightly simpler system solution with only a steam turbine and no gas turbine, the total electricity efficiency will be reduced to about 35 to 40%. Introducing a compressor cooler to provide comfort cooling, we would then arrive at a final total service to the end user equivalent of 25% of the fuel input as electricity and about 30% of the fuel input provided as cooling power. This technology can be combined with solid biofuels. You do not need a gasifier to make this kind of plants. But again, to keep up the total efficiency, the scale has to be around 200 to 500 megawatt thermal input. So, for biofuels, it would mean that the transport work becomes quite large. Going further down the scale, into units about 100 up to a few hundred megawatt thermal input, we will find technologies that are more suitable for biofuels. To keep up the total efficiency in the system, you would prefer to use a combined heating and power station, where you make use of the heat produced. In such a unit, you would arrive at an electricity efficiency about 35 up to 40%. When the heat demand is low, you would instead produce the cooling in this case by using an absorption cooling production. And that would ultimately give you a total final service to the end users of about 35% of the fuel input delivered as electricity and about 30% of the total fuel input delivered as cooling power. So you will notice that this is comparable to the large-scale unit that we had from the beginning. Even further down the scale, the electricity efficiency will decrease because of scale effects in the steam turbines. And at about 75 megawatt thermal power, we would arrive at 30 to 35% electricity efficiency. This is comparable to what you get from a nuclear power station. Using absorption cooling, this will then finally give a service to the end user equivalent to 30% of the fuel input as electricity, about 30% as cooling power, and you will also have a little bit of residual heat that can be delivered to produce hot tap water. Comparing the four different systems in one slide, You will notice that the two top ones, the larger scales, which are more than 250 megawatt thermal approximately, and typically fired with fossil fuels, are fairly inflexible. None of them can deliver any heat, but they can only deliver electricity onto the grid, and local compressor cooling machines are then used to provide the cooling needed. The two bottom ones, which are both combined heat and power production units, smaller scales at up to 250 megawatt thermal, will have a larger flexibility. They will be able to produce cooling, electricity and heat in varying proportions. So they will be more flexible, they will have a higher total efficiency, but they will still deliver energy services in roughly the same proportions as the two major power stations at the top. The numbers in the comparison are chosen so that the amount of cooling power delivered is the same in all four cases. And you will notice how the two CHP plants at the bottom can deliver at the same time different proportions of heating for tap water. So CHP is more flexible than condensing power production. Also, CHP would typically be used in smaller scales because you will need to have some place to sell the heat, and you cannot sell too large amounts of heat for district heating. So typically the CHP plants will be a bit smaller, and that will also make them more suitable for biofuel supply. By this, we have now arrived at the end of the course. Now it's up to you. How can you use what you learned in this course to contribute to spread the message and to counteract the common misconceptions and the common misunderstandings about bioenergy and renewable energy in your region? The aim of this course was to make you appreciate the real potential of renewable energy, based not only on bioenergy resources, but on the renewable resources best suited in your own region. You've learned a little bit of how to assess the resources, but you've also learned to take into account the whole system. However, we have not covered the different technologies for electricity production, cooling production, or heat production in any detail in this course. But hopefully you have learned a little bit to help spread the message and to contribute to a larger proportion of renewable energy in the world's energy supply system and in the energy supply system in your own country and your own region. You will be welcome to take other distance learning courses with the Department of Bioenergy Technology at Växjö University. Bye and good luck in the future.